Okay, well, thanks, Yahiro-san, for a chance to give a little explanation about this problem. We've actually had a lot of fun this week talking about the problem of the equation of state in the interior of a neutron star. You know, it's at a nuclear matter density, so 10 to the 15 grams per centimeter cubed. Also happens in the interior of a supernova when a star, say 10 times the mass of the sun, collapses the core under its own weight. It compresses to a nucleus of 10 to the 15 grams per centimeter cubed and induces the star to explode, we think. But even after 50 years of working on supernovae, the problem of how supernovae explode is still not understood. It's a rich problem, though. There's lots of particle physics and nuclear physics. And one aspect of the problem that hasn't been that well understood and that well explored is the effect of the nuclear equation of state itself. The part I'm talking about today, this is a picture of one of our supernova simulations. These are different radial zones moving out, and this is what the mass does in that zone as a function of time. The collapse to nuclear matter density occurs here and forms a neutron star of a radius of 10 kilometers. It's sitting here at 100 and then collapsing down. But it's the interior here that we need to understand in order to understand how this collapse sends a shock out that explodes the star. There's a conundrum in that, because as we learn about neutron stars and we learn about supernovae, what we need to get a supernova explode is opposite to what we see is needed to explain the neutron stars, and I'll talk about that. But let me say, until really just a couple years ago, there were only two versions of the equation of state that were used in supernovae to describe the interior. One is based on a relativistic mean field method, which is a way of, well, relativistically dealing with the meson fluid and so forth inside nuclear matter. The other is a more liquid drop, just the bulk properties of nuclei, their surface tension, their Coulomb repulsion, as the way it behaves as a liquid drop. There was a third equation of state, which is the one that we've used in our code since way back in the 70s, which is also a kind of liquid drop, but it's designed to be more phenomenological. What we have tried to do, I and my students, two of which got their PhD thesis working on this, is to actually modify the liquid drop approach into what's called a modified Skyrm density functional. In nuclear physics language, it's a way of solving the nuclear many-body Hamiltonian by replacing the nuclear forces with a delta function, a contact interaction, and then you get an analytic solution to, say the expectation value of what the energy density or the pressure is, as a real many-body solution to a very simple interaction. That technique has been around for years, and it's nice because it makes everything analytical functions of just the density of the nuclear matter. Let me give a little more background on the problem. This is a recent review of all of the known neutron stars in binary systems and pulsars, and we can measure their mass. And until very recently, we always thought neutron stars, we would always see them around 1.5 times the mass of the sun. But a couple of years ago, especially this object here, showed up with a very high neutron star mass. That turned out to have a big impact on our understanding of the equation of state, because almost, in fact, the two equations of state I showed you, one of them, and to some extent the other, would not have allowed a star that massive. We had to use a different version of the equation of state to get it right. What's important about this measurement, and there are two of them now, one of a 2.01 solar mass and one with, that should be 1.97. Yeah, oh, there it is, 1.97. Yeah, okay, there are three of them now. One at 1.91, 2.01, and one at 1.97. Is that they could be measured by two independent ways. There's a relativistic effect and just Kepler's laws. If you see a binary system and you apply Kepler's laws from the redshift velocity shifts, you can get the masses of the two stars fairly well, but it's ambiguous because of the inclination angle. But in this system, one could also see something called the Shapiro delay in this pulsar signal due to the gravitational potential of the secondary star. And that fixed the masses very precisely. So we have three systems like that now that show a very heavy neutron star. That requires a stiff equation of state. This is just a schematic calculation. This is parameter, it's the compressibility of nuclear matter. So we talk about how stiffly the nucleus responds to trying to squeeze it. And if this is a big number, it's stiff, and you can get a very massive neutron star before it collapses to a black hole. So it turned out now most of the other equations of state had values of like 220 MeV in units of this parameter. But now it turns out you need something more than 230. Let's see, the 230 line just barely gets there. So you need a stiff equation of state. And also there are constraints on the radius now that put it right about here. So even these are marginally consistent with observed neutron stars. This is a conundrum in supernova physics for the following reason. In order to get a supernova to work, you want it to collapse in this initial bounce to very high density and very high temperature. In order to get there, the equation of state has to be soft. It has to not resist too much as the star is collapsing down. That forces the neutrino temperature down here in this proto-neutron star to be very high. What causes the outer layers of the star to eject at first order is actually not the shock itself, which sort of goes up here and starts to stall after about 150 milliseconds. But up to about 200 milliseconds, it's the very high temperature neutrinos, 10 to the 53 ergs per second, being emitted from the proto-neutron star that actually reheats the shock and causes it to head out. You need a soft equation of state to get the temperature very high and the density high down here to get a big neutrino flux to explode the star. Also, there are heavy ion data that look at, well, there's several different aspects, but they look at kaon production and so forth. And that production is related to how stiff, as two heavy nuclei collide, how much they resist increasing the density. And they seem to favor a soft equation of state, but that's contradictory to what you need for a neutron star. So we have a conundrum in physics. You know, there's two aspects that need a soft equation of state, and yet nature keeps telling us, no, it's stiff. You can have very massive neutron stars. So one needs to go back and look at the general hadronic nuclear equation of state and see how to fix that problem. And I'll discuss the way we went back and looked at it. at first, in the general way, we do this equation of state. At low density, well below nuclear matter density, you just have a gas like the gas of particles in this room. It's just regular nuclei, but it's a higher temperature and density. So you have neutrons and protons, alpha particles, normal nuclei, and they actually undergo a nuclear reaction network and generate energy. Eventually, they get into something called nuclear statistical equilibrium, kind of like an ionized gas for nuclei. The reaction rates are so fast they don't matter anymore. The relative abundances are just given by a Boltzmann factor, like the Saha equation in atomic physics. Okay, so this region doesn't change much, but you want that overall to be soft. What happens that's critical is we make this transition towards nuclear matter density. Now, the way we solve the problem of keeping it soft is if you allow production of pions, that actually softens at high temperature the nuclear equation of state, because as the star goes to compress, instead of resisting that because you're trying to force the nucleons closer together, that energy just goes into producing more pions. So that's what softens the equation of state. But as the equation of state gets cold, you need it to be stiff. And in order to do that, we actually add a three-body nuclear force term that we deliberately force to be repulsive, and that gives us the right neutron star mass. Now, there's another interesting problem. Inside that neutron star that's forming, the density keeps increasing until maybe even 10 times the density of a normal nucleus. If it gets that dense, then you actually can, we think, make a transition from normal nuclei to a plasma of quarks and gluons. That has some effects on the equations of state. For one, if it's a first order transition, like a transition in ice, from water to ice, that's a first order transition. You have a latent heat, the pressure response goes away, and the equation of state will get soft again. And that could have some important consequences for supernovae. I'll talk about that a little bit. By the way, feel free to interrupt any time. This is just pedantic overview. So this is a little more detail, more for a nuclear physics audience of how, this is the low density region. All of the energy in most stars, when you do stellar evolution and also supernovae, you can describe with only 9 elements and 17 reactions. It's a standard of the field to do that. It gets a little more complicated. We have an ideal free gas. This is just a modified ideal gas law because you have a bunch of different components there. But there begins to become some Coulomb energy, kind of like a Van der Waals kind of correction. So we have to add that in. So that's how we treat it at low density. That you can't play with much. But it turns out the transition to when you begin to approach the density of an atomic nucleus, the saturation density of nuclei, it gets very critical in a supernova because it affects the development of convection. And I wanted to take a minute to go through that and show why that's so important. It's a crucial ingredient for the explosion. And this is a figure from one of our papers and our book, but there's a phenomenon that occurs as this neutron star is cooling. It's analogous to sometimes there's a freshwater river that's going into ocean water. Now, if I get it right, the salty water is higher density, but if it's warmer compared to the river water, then it actually can want to rise through the water, and you get this dendritic instability. They're called salt fingers when those two kinds of river water, salty water that's warm mixes with regular water that's cool. The analog in a neutron star is you have neutron-rich material. The neutron is a little bit, I have to get it right, heavier than the proton. That's why the neutron decays to the proton. So the low Ye material is heavier, so it wants to sink even though it's the warmer material. It gets warmer because it's heated by neutrinos. At the same time, the protons, which, let's see, they're cold, but they're lighter, so they want to go up, and it forms this dendritic instability. It's very dependent upon the equation of state, and I'll show you the details we have to go through to get it right. And it's also controversial because not every equation of state does this. This was a paper we did a number of years ago just to show how important this is. This is the neutrino luminosity versus time for the first 500 milliseconds. If there's no convection, the neutrino luminosity dies away. We added convection either by this neutron finger mechanism, this dendritic instability, or we added magnetic turbulence. Either one drives the neutrino luminosity way up, because if you have convection in that neutron star, it pulls the neutrinos up and gets that luminosity high, and that's what drives the explosion. So, for example, here's the velocity. Without convection, the star just collapsed back down, became a black hole. But with convection, it goes on and forms a regular shock. This is entropy, not as important, but the example of the temperature. Here's what you would have seen, if I could get it running, is this is before it collapsed. There'd be a neutron star forming. It has a lot of convection in the interior, and out here in the outer layers, there's a huge convection going on. And the problems with supernova explosion, where the field is now, is actually analyzing this convection to see both above the protoneutron star and below if there's enough neutrino heating to get it to explode. But let's move on to the next thing. As the density increases, you go from an ideal gas to a gas that's in nuclear statistical equilibrium. Simply put, it's a kind of Saha equation that I mentioned already, and it's only constrained by, the sum of the mass fractions is 1, so that's baryon conservation, and you have to conserve charge. That's what that reaction does. And what we do is we approximate it as a 4-component gas of neutrons, protons, heliums, and one average heavy nucleus. The reason is because it takes, even though it's a simple equation, it's a lot of time if you want to calculate for every temperature, density, and condition the entire range of thousands of nuclei that could be there. Although it turns out one needs to do that. So this just shows you kind of how that's done. An average heavy nucleus comes from sort of a kind of Thomas Fermi calculation. There's an analytic solution to that. That's the way we used to do it. This is a little technical, but basically the nuclear statistical equilibrium gives us an analytic solution for the mass fraction in baryons and protons, neutrons, alphas, and this heavy nucleus. To that we have to add a Coulomb term, which comes in here, and we have to add a surface term, which comes in here, that depends upon what the asymmetry parameter is. That was a simple way to do it, and in the calculations we did back in the 80s, 90s, and a decade ago, it's the way we did it. But we actually use something more sophisticated now. There's something called Wigner-Zeitzel, where you take this big many-body system and break it down into one cell of, say, hundreds of Fermi in size, and you start increasing the density by putting, neutrons, protons, alphas, and everything else in there. And then you'll get some average, you'll get a system that has nucleons, alphas, and heavy nuclei forming, and the nuclei will form bubbles, and how much the bubbles are formed, this is kind of messy equation. But there's just an effective Coulomb energy associated with the size of the bubble. And then there's a surface energy associated with the surface tension that relates to a parameter that relates to this asymmetry parameter. All that is kind of technical, but you actually have to go beyond that to do it right, because we know now if you look at one of these cells and start increasing the density, this is from a paper by Okamata where they did a kind of quantum molecular calculation. Nuclei can form, this kind of spaghetti structure or lasagna or spheres, but that's why it's called nuclear pasta. One can treat that analytically. There's basically this structure comes from the competition between the Coulomb force that's trying to force all these nuclei, they're compacted to get as far apart from each other as they can, but at the same time there's a surface tension that wants to minimize the surface area, and that leads to the formation of these complex structures when the system minimizes the free energy. Anyway, there's an analytic way to treat this transition through these phases, and we've added that. Okay, so that brings us through this transition region, and we're reanalyzing that to see how efficient the convection is. And it turns out at high temperature, this breaks down, the nuclear pasta breaks down into a simpler system anyways, and so you actually get this convection back because it's just driven by temperature gradient, just like boiling water on a stove. If you have a big heat source, in this case it's the neutron star and all the neutrinos coming up, it basically forces the neutron star to bubble, and it forces the material above the neutron star to bubble, so that helps the explosion. But the next thing is, okay, this is the sort of a canonical cartoon of as a function of chemical potential or baryon density, here's the normal nuclear matter I've been talking about, and then there's this transition to a quark gluon plasma. Now, neutron stars form down here somewhere, and it's not quite clear whether neutron stars will get into this region. But the protoneutron star also goes up in temperature in a supernova, so it has a chance to cross over this line even if the neutron star doesn't get there. So that turns out to be important for supernovae, as I'll go through. This probably I don't need to go through. It just explains how we treat the pion fluid as a non-interacting gas with a chemical potential and some effective mass energy, because the pion has an effective mass because it's in a nuclear medium, and there are many body effects that you can treat with this polarization parameter and something called Landau-Migdal theory, which is kind of antique nuclear physics, but it's a very interesting many-body problem. And this shows, one of our calculations, pressure as a function of the number density per Fermi cubed. Nuclear matter density is, it's actually about here. And as we increase the nuclear matter density, this decrease in the pressure actually helps a lot in getting the explosion to work. This is a picture of as the nuclear matter density goes from 2 to 3 times nuclear matter density, that the pion fraction goes up, and that helps us get the soft equation of state that we want. So now we're at the regime where we're above the nuclear saturation density. So we go from a gas of free nucleons, alpha particles, and some heavy nucleus to just a pure nuclear fluid. And we want to compress that. So here you need a solution to the full many-body nuclear physics problem of what happens in nuclear matter at high density. And neutron stars and supernovae and a little bit heavy ion collisions are the only ways we can probe that. This was the old way we used to do it. What I want to talk about is how we replace that with a Skyrm density functional theory. So this is a many-body Hamiltonian, just like an atomic system or a nuclear physics system, but you can have three-body forces in addition to two-body forces. Nuclei can have, easily you can draw a Feynman diagram for a three-body force. It's just two pion exchanges among three nucleons, for example. So the trick in density functional theory is to write this two-body and three-body Hamiltonian in terms of delta functions of the distance between the nucleons. And when you do that, you know, the integrations of the matrix element here become just analytic functions for nuclear matter. And you can write down right away the energy per unit mass is just given by the Fermi energy for non-interacting gas, plus these correction terms in terms of amplitudes of these terms of the delta functions in the nucleon-nucleon interaction. So this is getting technical and too many equations, but this free energy becomes divided then into three pieces. There's the nuclear matter interaction piece for symmetric nuclear matter, like normal nuclei. And then there's this correction as you get to very neutron-rich, neutron star-like matter. And then there's something that corrects for the fact that this is a very high temperature. This can be 10 to the 10th or even 10 to the 11th degrees as this star forms. So several, you know, tens of MeV in energy. Now, our approach to this has been to, let's see, the usual approach to a Skyrm model is to try to fit a bunch of known nuclei in their excited states, say, but we're really interested not in nuclei with all the surface effects, but we're interested in bulk nuclear matter. So we deliberately are picking sets of parameters that will fit what we know about neutron stars and what we know about bulk nuclear matter. So we force it to give what's believed to be the observed compressibility parameter that's measured by the nucleus has a monopole resonance, like a breathing mode. And you can measure that, and from that you get the response of the nuclear fluid to being compressed spherically, and that's that term. And we know the density of an average nucleus is about, you know, 0.2 nucleons per cubic Fermi, you know. So we force the parameters to do that. Then there are some constraints from heavy ion physics and different nuclear matter determinations. I'll show that in a second, but basically by forcing these values of the nuclear parameters, we actually can fix all of these parameters of the Skyrm interaction to get the right compressibility, the right the binding energy per nucleus, etc. And the only thing is there's a three-body term embodied in this sigma piece, which shows up here. That's the three-body term. And in fact, once you fix these parameters, you actually fix this power law for the three-body term. Okay, so the real problem is once you understand symmetric nuclear matter, because that's what we measure in heavy ions and nuclei, you need to extend it to pure neutron-rich matter, and that is this thing called the symmetry energy. Yp is the fraction in protons. So as this goes to zero, then you have neutron star matter. There are constraints on that. The symmetry energy can be analyzed in a Taylor series in terms of a linear term and a quadratic term. And people have gone out and tried to measure that. Heavy ion collisions tell you that the value of that linear coefficient looks like this. There are measurements of what's called the isobaric analog state in nuclei that sort of puts it here. These are measurements of something called the pygmy dipole resonance that depend upon that. Nuclei have a kind of a vibration mode in which the charge separates. You know, neutrons go one way, protons go the other way, and there's a subset way of that. And that's just a calculation from a model. But all these together put a constraint on what this L parameter can be. This is an example from a paper of a whole bunch of examples, but there's a constraint also from this isobaric analog state of this surface asymmetry as a function of density. So we basically have adjusted the parameters of this Skirm interaction to run through that constraint from the isobaric analog state and also to match the constraints on this linear term, plus all the other nuclear matter. And okay, those are just numerical values. So in the end, we end up with the symmetric nuclear matter, normal nuclear matter. It's about 30 MeV. And so we think we have a reasonable handle on what's going on inside the neutron star, having redone our equation of state. The third thing is, and final thing, I know I'm going kind of long, is what happens when you get to much higher baryon density. I actually sketch on here, this is what we were talking about, since this is in units of baryon density, so there's normal nuclei here, and temperature, I could actually take one of our supernova simulations and see what happens on a plot like this in a phase diagram. And basically, as the proto-neutron star forms, the temperature starts going way up to like 50, 100 MeV, and the density continues to contract to several times nuclear matter density. And somewhere out here, you can cross over into this quark gluon plasma regime. And like I said before, once you're here, then the neutron star will spend actually thousands of years cooling down and may actually go back out of that. It may be the only time we see quark gluon plasma is during a supernova. This turns out to make a big difference in the evolution of a supernova. My student Nick Gentili and I did this already 20 years ago, more than 20 years ago, but then everybody forgot about it until a couple of years ago. But what happens is, if you look at the pressure as a function of density, if you go into a first order phase transition, instead of the star responding, it just switches from normal hadrons into quark gluon plasma, and the increased pressure actually goes into latent heat of this transition. And so basically the pressure response of the star in terms of a power law and density gets very small while you're making the transition. But then once you form quark gluon plasma, it goes way up again. So a second order transition, the star gets very stiff right away. The pressure response is high. But in a first order, it actually loses its pressure response and goes into a second collapse to form a quark matter kind of star. And what we showed way back then is you get two shocks going out, but they were separated by a very slight difference when we did the calculation, but we didn't do the neutrino transport right. That was redone just a few years ago by Sargert and others at the Max Planck Institute. And when you treat the time scale for neutrinos to go through the star as this happening, it turns out you get two shocks that are separated by about a couple hundred milliseconds, which is exactly the time scale that you want to rejuvenate the supernova shock. And in fact, when you put that in, they found, and so, well, yeah, they found that a star that doesn't explode, if it makes the QCD transition, it will explode because it has 2 shocks, which is enough to give it the energy to keep going out. So we went through making our version of the QCD equation of state. You construct a thermodynamic potential. It's in Landau and Lifshitz. It's a little different than the free energy I was talking about before, but it's related to it. So usually people just included the 0 non-interacting quark gas. We decided to add the 2-loop corrections to the quarks and gluons. And then in a bag model, you have just a general QCD vacuum energy from all of the loops of gluons that can go around this system. And then people are interested in the possibility of color superconductivity. So that was easy to add. You just have a gap parameter, just like in BCS theory. It's just a different value. You put all that in. You know, those 2-loop corrections look kind of complicated, but it's just straightforward integrations over the phase space. And those have all been worked out by Glenn Denning some years ago. So we added this equation of state. We can fix the bag constant from lattice gauge theory, even though it's in the high temperature limit. We worked out a number of years ago, probably a lot of people have, but in terms of the quark and the hadron degrees of freedom, the temperature of the high temperature phase transition, that is the low baryon chemical potential limit, is directly related to the bag constant, so puts a constraint between 170 and 240. So with all that together, then we went back and recalculated properties of neutron stars. So for example, like many equation of state, our old one from 1993 doesn't make a 2 solar mass star. It makes only about a 1.7. So that's ruled out now. We can't use it in our simulations anymore. But the new one that we generated is this one, even if we just use the hadronic part. Let's see. Yeah, then we can get to 2 solar masses. If we add a simple crossover QCD transition, then we can get very high. Or if we add one with a bag constant of at least 220 MeV, then we can get up. It actually softened it a little bit to about here. So anyways, we have a favorite QCD transition. So what we're working on now, and this is the last slide now, is putting all this together and seeing how it affects the collapse. And this is our preliminary result. We ran the same code with the old Bowers and Wilson equation of state, and this is the figure I keep showing over and over again, but now it's on scale only out to 500 milliseconds. We ran it with the new equation of state. This one does not yet have the quark gluon plasma in it yet, so there's only a single shock, but even with all of the new hadronic physics and a much stiffer equation of state, we get almost exactly the same explosion. In fact, if you look at it in detail, the kinetic energy of the explosion actually went up a little bit. We thought it would go down, but so it's still a robust equation of state for getting the explosion, as long as the convection is turned on. And it allows for high neutrino temperatures at late time, which is why it works. And with that, I'll stop and see if there's any questions. Thanks.